Hello, everyone. I hope you're doing well. So, for today's class, we are going to proceed from where we left. And the previous class we did circuits for a half adder. This is a circuit that is able to um, compute or add two bits, and a bit is just one signal. So, adding two of them and getting an output and a carry. We also were able to count signals. We did a delay line. A delay line is a circuit that is able to output the signal but delayed by several ticks. And we saw that in the future we're going to see how this is important in creating memory. And we did double the number, which is able to do a multiplication on a list of or a series of bits and double them to a higher number. For today we are going to finally do a full adder, which is essentially able to do an operation on a byte of data, which is 8 bits, and go on from there. So in the previous level, we are able to add two inputs. This time, we add three. Once again, add the inputs together in binary such that the result is either 0 or 1. As with normal addition, the result cannot be described with one digit. If the result cannot be described with one digit, do a carry. I think necessarily a full adder in this case has 8 bits, so my previous statement is not necessarily correct. And so let's do the half adder was something like this. We had an XOR. We also did have an AND gate. And an AND gate to get the carry. So but now we also have another bit, so we'd probably add again this using an XOR. And maybe another AND gate. I'm not really sure. Or instead of doing this, the XOR is able to do the maths. So let's just try and undo. We can have this going to the sum as we did before, and then we can have our AND gates to pick the carry from the first and the second bit of data. And then we can have another XOR gate, but this one is going to be between the first 2 bits data and the last one, which is this. Let's try and extend this a bit. And so it's the first one, assuming this is the first, which is representation of these two, and the second one. And also again, from them we can derive a carry. Carry is derived using another AND gate, which is between the first one and the second one. And now we have 2 of these. We can now find a way to we can now conclude that this is able to give us the sum, since it has already taken the 3 bits and XOR. And then to add these 2 to get the carry, we can just use an OR gate between this and this other one, and this should be our full adder. So let's try and see if that works. Yeah, that works. As we can see on this circuit, to get a sum, we just use an XOR gate. To get the carry from there, we use an AND gate, so we have this carry. And then after that, since we have another bit, we need to chain it together. So the output of these 2, again we XOR, assuming it's just like 1 bit, and then the input of the third one is just the same. We use it on the XOR gate, and again we get the carry between them and OR them. So you can see a pattern here. So if we have another bit here forming a nibble, we would have another XOR gate, but now between these 3, these three, which the output is here, and this one, we get another XOR gate to get the sum, and from both of them, that and this, we do another AND gate, and now we can OR all that together to get the sum and the carry. So yeah, and we can, and now we are given a new component that's a full adder that we are able to do. It says that the adder, it's a 3 bits, adds 3 bits and outputs the sum and carry. That's exactly what we implemented here. After that, we have this level called odd ticks. So in the previous level, you learned how we don't allow circular dependency. That was the issue that we showed, that circular dependencies, it's not really expected. It's a wrong way of wiring the circuit. So in the previous level, you learned how we don't allow circular dependency. Now you must learn the one exception. Okay. The delay line is allowed to depend on its own output, on its own input. This is because the input does not influence the rest of the circuit until the next tick. Oh, okay. So only when the delay line is used, that's when an component relying on its own outputs, or I think output is an issue. It causes a circular dependency. But since everything happens under one tick, on one tick, a tick is a cycle. So, but since a delay line is not really, kind of holds the signal and outputs it on the next cycle, so that means that it doesn't really get influenced by the circular dependency. So this is the exception that we're being told over here. So says the square pins in the game never affect the output in the same tick. They therefore never cause circular dependency. Continue. Outputs are red, which is false, on even ticks, and green on odd ticks. So we're detecting odd ticks. 0 should be odd. Yeah. So, and we already know, we have a hint that so that is the 0th tick, and next tick is on, but our output is off. Our input is off, but we get an on. So that means we need something that is able to turn it on. And that will be something like this. Oh, that's a circular dependency. So what if we place this here and this here? That's a circular dependency. Circular dependency is gotten when we have conflicting signals. Like on this same line, there is also there is one side is saying that it's on and the other one is off, so that might cause it. So let's start again on the zeroth. On the zeroth signal, and then we have to do this. On the zeroth, we have zero tick, we have 000, and but this one negates the line, and now we have a signal that is being delayed. So when we go to the next one, then this will be outputted over here and turn this on. So okay, what's that about? The problem is that, yeah, it conflicts with this. This is off, but this line is now turned on. So we are able to move just 2 ticks. Oh no. This line is on, so this is on, but this is off, so that's an issue. Okay, so our first tick, everything is off. Our next tick, our desired output should be on. That means that maybe the signal should oh no. when we get started, the output is this, which is wrong. That means that it should be delayed, and by delaying it, we delay it. Okay, let's start again. Input is off, output is off, which is okay. But now, since we had this inverter, we now are holding a signal which is true, and when we move to 1, the first tick, we have our output as on. But now this should be off so that it influences this. So that means maybe I need another, I don't know, another delay that's able to influence this, like in this way. So first output 0 0, so we have this held here. Next, which is odd, we have our output, but now this influences this, or this does not influence it right now, but it holds a true, but which in the next tick will influence this. Okay, that's tricky. This should go off, so how? Our first tick, we have the signal held by this, so the next tick should influence this and turn this on. But the problem is that since this is not on, it's going to, since this is not on, it's going to cause an issue. So I think we just need another gate, which is an OR gate between this and maybe this. So on the first tick, we can have it navigate over the next tick, it lights up, but now since we have an OR gate, it doesn't conflict with this, it influences that to the next tick, and the next, and the next, and the next, and the final one. Yeah, so that OR gate is the one which was able to help us detect odd number of ticks. And yeah, that's about it for the level. And I think we'll do the next one, which is bit switch and this bit inverter on, or rather in the next class. So see you in the next class. Bye.